In section 6.2, we're going to talk about another sampling distribution. But before we do that, we have to introduce a new symbol that we have yet to talk about in this class. We've often used the symbol of p to stand for a probability. You might recall that we used that when we talked about the value of p in a binomial distribution. But here, we're going to see that we're going to draw a difference between p here, which may stand for a proportion or a percentage of an entire population, and a sample proportion, which we will call p with this little caret on top of it, or what's called as, or read as p hat. Now, this is actually surprisingly simple. Again, if p stands for a percentage of a population, so maybe I want to know like percentage of all the people in the world that have blue eyes, that could be represented by p. But the value of p hat is just going to be a percentage of a sample. Like what percentage of people in our class have blue eyes? So there's a difference between the use in these symbols. Now, of course, to get a percentage is very easy. Just think about how you calculate percentages like when you get a test back. You just take the number of points that you've earned, which can be represented by this little x, and you divide by n, which is the number of points possible. Or what we would say here, x is the successes, the things that were successful, out of the sample size or the total number of things you were trying to achieve. So what we're going to see here is that p hat is going to, again, act as a random variable, much like x bar did in the last section. That is, the values of p hat are going to vary as I continue to grab different samples. To get a sense of how this is going to work, let's take a look down here at example 1, and we're going to go back and start to talk about a deck of cards and an experiment that we might be able to potentially run with them. So, as I state here, how exactly do the values of p hat behave in a given experiment? Well, I'm going to have another deck of cards that we're going to work through today. You might recall that a deck of cards has these different card values in there. Okay, so I have cards from an ace all the way up to what I call a king. I have these 4 different suits, 52 cards in total. 4 cards of ultimately each type of value. So what we're going to be looking at here is we're going to be trying to break these down into different suits. So that is the symbol that's based on them. So I have 13 cards in there that are spades, and 13 that are hearts, 13 that are clubs, and 13 that are diamonds. And my goal would be to construct a relative frequency distribution for the colors. Well, calculating that out here isn't actually difficult. In fact, I've already gone ahead and done it for us here. Because if there are 13 in each category, then there's 25%. 1/4 of all the results occur in each category. So if I was going to describe the shape of this distribution of suits, I would very easily be able to say this is exactly uniform, right? Every category has the exact same relative frequency. So we're going to be interested in what happens as we begin to take samples of cards out of this deck. Now, to see exactly what we're going to look for, let's take a look at the next part. Suppose that each of us was going to go to this deck of cards, and we were going to take a sample of 10 of the cards out of the deck. And we're going to compute the percentage of cards that we ultimately draw as hearts. Now, I'm going to imagine that we draw each of these cards kind of like one at a time. So like I'm going to pull one card, I'm going to record if it's a heart, shuffle everything back up, draw another card, and do this 10 times. And at the end, I want to know what percentage of the time I actually got hearts. Now immediately I can see my values of p and p hat actually coming into play here. In this case, if I look at the total percentage of cards in the deck, I can see that that value is actually just 25. So my value here of p is 25. 25% of the cards in the deck are actually hearts. But what happens when I take small samples? Let's see what begins to take place here. I'm going to go ahead and actually go back to my deck of cards that's here and see what happens as I continue to take some samples. All right, so let's see. Let's suppose I have my 52 cards laid out here, and I pull a card out from the deck. If I pull up that card, so far I have 1 heart. Let's keep going. Now I'm going to see that, I pulled a second heart. Now, I didn't get a heart, so far I have 2 hearts. So far I still have 2 hearts. Still 2 hearts. Now I'm up to 3 hearts. 4 hearts. Still at 4. still at 4, and the last one still at 4. So I only got 4 hearts out of all 10 pulls that I just did. So if I was to go back here, I could see that I could start to kind of shape this up on like some sort of a dot plot. So that is, I could state out here that I could have gotten anywhere from 0 hearts up to 10 hearts. Now, I want to write this as a percentage, so I'm going to say I could have gotten anywhere from 0% to 100%. And so 50% would fall right here in the middle, and we got something like 4 out of 10, which was 40%. So let's see, let's say this is 10, 20, 30, 40. So I'm going to go ahead and I'm going to put a dot right here. We got a 40%. Well, let's see what would happen if we say, did this again. All right, let's try to do this one more time. All right, so 10 pulls, how many hearts do we get? Okay, no hearts thus far. Still no hearts. Now I'm up to 1. Now I'm up still at 1. Still at 1 again. Still at 1. Now I'm finally up to 2. Still at 2. Still at 2. And we ended at 2. So there we got 2 out of 10, or what we would call 20%. So we can see that we could maybe imagine continuing to do this and labeling out all of the different results that we would get. And so our question would be, I wonder what would happen if we filled in a big picture like this. What p-hats would be the likely ones, right? Because what I've seen here is I got a first p-hat. This was p-hat number 1, and this was p-hat number 2. Number 2. And so I had a 40% on the first time. I had a 20% on the next time. And so definitely my p-hats are not always the same as my p. When I take a sample, sometimes I might get something lower, something higher. Just depends. But what we might want to see is which p-hats are the likely p-hats and which ones are not so likely. Well, we're going to go ahead and actually see how we can see how the values of p-hats begin to behave, and to do this we'll look at another simulation. Let's go ahead and take a look over here at this applet that we've used before. I'm going to simulate pulling cards out of a deck, and I'll start here by stating what are the probability of, I guess not pulling heads, but like probability of getting a success. What would be the probability of getting a heart on any given pull? Well, we already saw that 25% of the cards in the deck were hearts. So on any pull, I should have a 25% chance to pull the thing that I'm looking for. Now, sample size, we were going to do 10 cards at a time. And so we can kind of imagine simulating this. Here it's simulating with a spinner. Like, let's suppose that if it lands in the blue, that means I picked a heart. And if I didn't land in a blue, then I didn't pick a heart. So here I can see that, like, on this attempt, I only got 1 heart out of 10. Now I'm going to turn this into a percentage. So you can see I got 10% success, or 10% of the time I got a heart. But I, of course, could keep doing this, right? Like maybe the next time I got 4 out of the 10 are hearts. And the next time I get another 4. And I could start to see that as I keep running this experiment, some things will happen a lot and some things will not happen a lot. And so what we'd like to do is to start to see the general pattern. This, of course, will be a lot easier if we increase our number of samples. So why don't I do this? Now I've done this so many different times and I can start to see something. What kind of shape does my distribution begin to kind of have? Well, you might be able to get away with almost one of 2 shapes here. You could kind of say it looks pretty bell-shaped or symmetrical, but it might also be slightly skewed off to the right. So down here, I'm going to say the shape of the distribution is, I'll say, roughly symmetrical / bell-shaped. Or maybe we could say skewed to the right. Now in terms of what's most common, if I go back to that picture, it seems like things in the area of 20% or 30% were actually the most common. And that's maybe not too surprising, again, considering that we actually know that 25% of all the cards in the deck were actually going to be hearts. So it'd probably be pretty typical to get about 25% of your cards being hearts. And that's what we see here. We get a lot of 20s and a lot of 30%. Okay, Well, what if we were to go ahead and continue to repeat the process? Does the shape begin to change? Well, what I'll see here is that as I continue to do more and more and more and more samples, the shape still continues to be pretty much bell-shaped. So I'll write that here. The shape is still very bell-shaped, right? That seems to be the case. And 20% and 30% seem to be the most common results. Or I'll say here the most common p-hats that I can end up with. Okay, so what about part F though? What seems to happen to the distribution of p-hats if we were to repeat the experiment, but maybe we took more cards out of the deck every time we computed our sample? Well, let's see what would happen here. What if instead of drawing 10 cards out of the deck, I drew 15? Well, if I was to do this, I can start to see first off that some new percentages are going to be possible. If I'm pulling 10 cards out of the deck, I can only get percentages of like 10%, 30%, 70%. But if I'm doing things out of 15, I can get weird percentages with like awkward decimal amounts. And so I can see here on my number line, some different percentages seem to start popping up. Now I'm going to actually show here some summary stats to highlight some things. I can still notice that my average here, as I continue to do this, is still going to be that I get an average success rate of about 25%. So on average, about 25% of the cards are still going to be hearts. And I get my standard deviation here around 0.111. Well, notice what happens if I start going to 20 cards out of the deck. Now, if I do this a bunch of times, what I'll see is again, hey, my average success rate is still around 25%. My standard deviation is maybe a bit smaller. I can see that if I went up to like 25 cards, or maybe if I even went up to 30 cards, and I did this a bunch of times, I'm still getting an average around 25%, and my standard deviation is going smaller. And actually, in all of these cases, I can also see that my distribution shape is actually looking more and more bell-shaped. So I'm going to go ahead and summarize this here. As n increases, remember n represents my sample size, the distribution, 1, has a shape that is more bell-shaped. It starts to kind of become less skewed. I can see that the average of my p-hats, like the typical p-hat, is always around 25%, which very interestingly, remember, was exactly the percentage of cards in the whole deck that were actually hearts. And the very last thing is I could say that the standard deviation continued to get smaller. So these were kind of all interesting properties that were true. And actually, these are properties that we can summarize in the sampling distribution of p-hat. So if p-hat is a random variable, what shape does it form? Well, we can see that as I start to make my sample larger and larger and larger, I get an approximately normal distribution. However, I can say that it'll be so close enough to normal, for all practical purposes it will be normal, if I can satisfy these two conditions. One relates sample size to population size, and another relates this value of n and this value of p, like this p value that I have here. We'll talk more about these in a future video. However, if both those conditions are met, then p-hat will have an approximately normal distribution, with my average of p-hat being equal to p. That's what we're seeing here. My average of p-hat was always around 25%, which was exactly p, and my standard deviation of p-hat is given by this. Notice though, as n, the value of my sample gets larger and larger and larger, the number of items in there gets larger, then this whole value will continue to get smaller and smaller and smaller, which is exactly what we saw here. As the n increases, the standard deviation continued to get smaller. And again, I can replace these values here with what's happening in this z-score formula, and I get something that ends up looking like this. Now we'll cover all of these ideas and recap them in the next video as we start to see how we can put this together to calculate some probabilities in example 2.